Hello everyone, Jack here from Disseminate the Computer Science Research Podcast, and welcome to another episode of our Cutting Edge series. We're going to be talking about networking today, and specifically we're going to be talking to Gina Yuan, who will be telling us everything we need to know about her recent NSDI paper, Sidekick in-Network Assistance for Secure End-to-End Transport Protocols, which won 2 awards actually at the conference. It won the Outstanding Paper Award and the Community Award, so that's awesome stuff. Gina is a PhD student at Stanford University, where her research interests are building systems and designing algorithms for networks. Welcome to the show, Gina.
Thanks, Jack. It's really great to be here, and thanks for the introduction.
Awesome stuff. I'm really excited about today's podcast. This paper is absolutely jam-packed with really cool stuff, and a lot of acronyms as well. So we're probably going to have a breakdown of a few of these acronyms throughout this conversation today. But let's start off, as we always start off our podcasts, by getting you to tell us your story.
Yeah, currently I'm in my 5th year of the PhD program at Stanford. Before that, I was at MIT for my undergrad and my master's degrees, also in computer science. Outside of that, I like to run and bike. But how did I get into systems research? First, how did I get into computer science? I think in undergrad, I didn't really know what to do at the time or what I wanted to do. So I kind of just did what I thought was cool. And I think everyone is really getting into computers at that point. And I applied to a few clubs at MIT. I applied to the trading club and I applied to the Hack MIT clubs, and they both rejected me. And so I ended up having to do research, darn. But I really started getting into computer science because MIT had this UROP program, which is an undergraduate research program. And I wanted to have some academic extracurricular. So what I did was I just emailed a bunch of people and only a few got back to me. And that's just how I got started in research. But actually, the first research I did as a freshman was not really research because I didn't really know anything about computers. But I was building apps, basically. I built an Alexa app. I built JavaScript apps. But I learned a lot about coding and engineering during this time. And this really set the foundation for me enjoying building systems and writing code. And yeah, that's how I got into systems.
Awesome stuff, yeah. Just kind of jumping back a second there, you said that there's this concept of applying to clubs, MIT, and they accept you or reject you. That's such an alien concept. We had societies in universities in the UK, but they were just happy normally for people to come along. Maybe it's a different sort of structure in the States.
Yeah, maybe it was even that the fact that you had to apply made it seem even cooler because then you could be part of this exclusive club. But, I guess they need like a few people to run the organization. Then it becomes a tight-knit community, but yeah, had to apply.
I kind of see it from the sports. I'm getting kind of waylaid a little bit now, but I see it from the sports perspective when you've only got like a set number of positions on a team, right? Like you've got a trial and et cetera, et cetera. But yeah, I know like the maths society or the computer science society at the universities I've attended are always like happy for more members, right? More people to go and get drunk with on a Wednesday night normally.
College.
Exactly, right, yeah. But that's interesting. And also as well, when I was doing some sort of my background research on you, Gina, I noticed that you ran something called Battle Code, and this was new on me. So can you maybe tell us a little bit about Battle Code real quick?
Yeah, it's another one of those clubs at MIT.
Okay.
This club creates a programming competition where you write code for these virtual robots, and then these virtual robots fight another team's virtual robots in this virtual world. And every year the game changes, and I kind of forgot exactly what the game was in the years that I did it. I kind of remember like robots that shoot bullets and then they hit trees, so it's not too violent because they're trees. And yeah, like you form teams and then there's brackets and there's live tournaments and you commentate them. And so I just started one year like competing in it. And then the next year, because I had so much fun competing in it, I ended up joining the organizing team for the club and leading it for a few years. Yeah, that was a really fun experience and also very systems oriented because now I was like touching all the like infrastructure in the cloud and just like writing code that all these people were going to use and iterating really fast because it wasn't like a company. It was just a bunch of like grad students and undergrads at MIT writing some code for people to win like thousands of dollars.
That's a big prize as well then, yeah.
Yeah, just
Nice.
some students writing some code.
Yeah, that's good. It reminds me like I guess the virtual. I don't know if you ever had this in the States, but it's called Robot Wars. It was a big thing when I was a kid. People would basically build a little like a. I mean, these things are pretty gnarly actually. Like these little like robots, and they'd have like axes on them and stuff. And then basically you'd build your robot, and then you'd compete against somebody else. I mean, I can send you a link on YouTube after this so that you can see Robot Wars in action. Because I'm probably not going to do it justice. But yeah, basically you build a robot and you try and destroy somebody else's robot, basically, like a little thing. But anyway, it was cool. We used to love it as kids. But anyway,
Yeah.
let's get back on topic. So let's talk about your paper and your research and networking. So let's set some context for the chat today then before we do anything else. And yeah, tell us all about kind of what your research, kind of the area it's in, and this kind of canonical model of the internet, what performance enhancing proxies are, and yeah, tell us all these important terms we need to talk about Sidekick.
Yeah. And definitely stop me if I say a term that I've not defined well. Yeah, so my research is mainly in computer networking and systems. And when I tell people about networking who are not really familiar with networking, I kind of just talk about the internet. Anything we do on the internet involves a computer network. So I like to think of the network as a collection, like a network of nodes with links connecting these nodes. And we want to send data from one node in this network to another node in the network. All the nodes on the edge of the network are like our end devices, like our computers, our cell phones. And the whole goal of the internet is to be transferring data across these nodes in the way that we want them to. This paper is related to something called PEPs, Performance Enhancing Proxies, PEPs. And before I dive directly into what PEPs are, I kind of like to start talking about my paper by talking about a problem that we are trying to solve that feels real to people. And so this problem is like, imagine you're on a moving train and your laptop is connected to the Wi-Fi on this train. And then you're connected to this Wi-Fi by connecting your laptop to a router. And then this router in turn connects you to the rest of the internet. And it probably has like a cellular connection or something like that. So if you were to use the Wi-Fi on the train, you'd probably think it's kind of slow. This is common experience, slow internet. But what does it mean for your internet to be slow? Okay, yeah. So imagine you're on this moving train and your browser is uploading a really large file to the internet. Your browser is doing this using something called a transport protocol. And some of these popular transport protocols are TCP and QUIC. So TCP might be the transport protocol that if you've taken a networking class or kind of just interacted with networks that you've probably heard of first. This was kind of the original transport protocol. And then QUIC is this new transfer protocol. It was invented at Google in 2012. It does a lot of the same things as TCP. It helps you have reliable connections, and it just forms this idea of a connection to begin with. And so the surprising thing in this imaginary train scenario, your laptop could be uploading large file using TCP, and that connection is actually very fast. But then your upload using QUIC is actually very slow. And this is kind of surprising because TCP has been around since the beginning of time. And then QUIC is a really new transport protocol. Yeah, so what is different about TCP and QUIC? And the main difference between these two transfer protocols is that QUIC is a secure transfer protocol, so it's completely encrypted on the wire, versus TCP has some unencrypted information, like the metadata in its headers, such as its sequence number. So every TCP packet has like a different consecutive sequence number assigned to it to ensure that they're all arrive at the other end host. Yeah, so transport is end-to-end for secure protocols. And this is kind of how the internet was designed to be. There's information in these packets that your routers, middle boxes, proxies, these are all going to be the same thing in case I use these words interchangeably. These middle boxes were not intended to participate in transport. And that's kind of how it is for QUIC, because everything's totally encrypted. But sometimes your connection can actually be better if you do know things about what's going on in the middle of the network. And so they could be better if transport wasn't end-to-end. For example, in our train scenario, we have like two different path segments going on in this connection. We have the one between you and the router, which is very short, but you might have a lot of wireless loss. But you also have one between the router and the rest of the internet, which can be long, but also more reliable. And so because it actually can be better for these middle boxes to use information about what's going on in the middle of the network, since TCP has these unencrypted transport headers, actually what a lot of these middle boxes do is that they will look at this information and use it to help your connection. And so this can be really great because these performance enhancing proxies or PEPs that are looking at your TCP connection can actually help you. But at the same time, they're going to be like changing the data on the wire, and then your transport is not going to be end to end as originally intended. Yeah, so that's the great part about PEPs. You can have awesome performance with PEPs, and they're widely deployed. They're deployed on 20 to 40% of internet paths, and almost all popular cellular companies will probably be deploying a PEP on your path. So this is the great part about PEPs. Yeah, one might ask now, then why would you invent QUIC if PEPs are so great? And because there's also a bad side to PEPs. And yeah, when I talk about the bad side of PEPs in my conference talk, I put up this slide with like a graveyard of tombstones. And then on each of these tombstones is like a different idea that has been, killed because PEPs are so bad. Or not so bad, but like because PEPs exist that the way they are. So in your head, imagine this graveyard. And then now we have some of these tombstones. So some of these tombstones have these great ideas for TCP. So like changes to TCP, extensions to TCP. Some of these include ECN++, TCP crypt, multipath TCP. These are all ideas that have been really hard or maybe even impossible to deploy. And this is because PEPs, in helping your connection and modifying your data on the wire that they weren't originally intended to see, they've kind of come to expect these packets to be formatted a certain way. And so now this expectation has been put in place and you can't change this format anymore. And this is something that's called protocol ossification. Yeah, so protocol ossification. Protocols have become fossils that are like not able to change or upgrade anymore. And that's terrible because our internet has changed a lot in the past few decades. Yeah, the other half of the tombstones are some of the research ideas that have been previously discussed to try to solve this problem of protocol ossification or of performance enhancing proxies not being able to help secure transport protocols like QUIC. But in the end, a lot of these ideas end up co-designing the protocols and the PEPs or explicitly credentialing these PEPs to have access to certain fields on the protocols. And we kind of feel like these solutions, while they enable performance enhancements for secure transport protocols, they kind of result in the same problems of ossification as before.
That's a fantastic explanation there, Gina. So kind of when you started giving this example and you was like, oh, the train Wi-Fi might be a bit sucky. Like that is the like my experience on all of the networks on the UK rail network. All of the Wi-Fi absolutely sucks. Like it's terrible. So yeah, they need to do something with that. I don't know what it is, but like it kind of sucks. But okay, cool. So I'm going to kind of relay kind of a few things you said to me kind of while you were describing that there, to see if I can kind of grasp this sort of. So ideally, or kind of originally, the proposal was that these hosts would not be end to end, right? So the kind of middle boxes don't necessarily they're agnostic to kind of what's getting passed through them. They're just sort of, they're agnostic to the things they're doing, right? They're just passing the packet along to the next host. Obviously, the topology of the internet is very heterogeneous. There's, like you say, there's like cellular, satellite, or whatever, and there's various different sort of these ways of these paths on this network and they have different properties. So we can use sometimes it's good to use these PEPs, these performance enhancing proxies, if they kind of can be aware of the path they're on, they can do smarter things to kind of make performance better. But that comes with the caveat that they make assumptions about, or they kind of change data in a way that then stops us actually, it becomes to that problem of ossification, right, where they're making assumptions and changing things, which kind of stops future development or kind of stops things kind of happening, or like the graveyard of research ideas of things people tried to do, but they can't do because of PEPs, right? And QUIC, which is, what does that stand for, by the way, QUIC?
Stands for Quick UDP Internet Connections.
Okay, cool. So that's a pretty new protocol, which sort of takes PEPs back out the equation by encrypting things so they can't obviously peek inside and meddle with the packets. But then that obviously stops us getting the benefits of PEPs, and it can be slower because I guess there is overheads with encryption and whatnot to do that. So that kind of maybe can make things a little bit slower. So PEPs are good and bad at the same time, I guess. And your work is going to allow us to get the best of both worlds, I guess, is the sort of way I've kind of the intuition I'm kind of getting from this. But yeah, in your own words, and give us the elevator pitch for Sidekick and what the goal kind of is.
Yeah, the elevator pitch would be it's a way to have a universal PEP. It's a way to help, for a PEP to help any transfer protocol that's already out there, and for all these transfer protocols to be able to keep changing and keep upgrading and evolving over time.
Love that. That's great. So let's talk about how you went about achieving that then. So in your paper, you sort of break this down into 3 technical challenges. So first of all is something called quACK. So tell us about quACK.
Actually, well, before even quACK, just the idea of a sidekick.
Yeah.
And so the idea of a sidekick is, instead of how PEPs exist today, which is actively manipulating your data on the wire to provide better performance, the idea of a sidekick protocol is for the PEP to instead send information back to the end host about the connection. And then the end host is making the decisions that will result in better performance. So the active manipulation of data happens at the end host and is end-to-end as originally intended, versus the proxy or PEP only observes the data. So that's the idea of the Sidekick protocol. Now, the first challenge was, our solution is called a quACK, but what was the challenge? The challenge is, what are you actually sending on this Sidekick protocol? So what can you send that is useful information about the connection back to the sender or to the data sender? And the way we think about this is something that's already been a very useful signal in these transfer protocols is an ACK. So saying which packets have been received for that connection at that specific node in the network. And so the proxy could just say which packets it has already received from that connection. Now, why is this a challenge? If you have so let's think about how you would do this for TCP. So for TCP, it's kind of easy because TCP has the sequence numbers that I mentioned before. Each packet is numbered consecutively. And so you can easily say as a proxy, for example, I received packets 1 through 10. And I also received 13 and also 15 through 27. So you can say this pretty concisely. But now if you're using QUIC and all your packets are totally encrypted, your packets look like total garbage, you don't know, you just can't express that you've received a range of packets, or even if any of these packets are missing because you don't know what the consecutive order is. And so that's kind of where the idea of the quACK comes in. We wanted a way to be able to concisely acknowledge a set of completely random looking packets. And there's several properties that we need to make this practical. It can't take up too much space on the wire. It has to be really fast if you're processing lots of packets at the same time. And if you lose any of these like quacks on the wire, you need to be able to have the same kind of correctness guarantees as before. That's kind of what we needed, but how did we actually do this? And I can talk about the origin of this later, but it took a lot of different connections. But our final solution at the end was, we realized that there's this related theoretical work in this idea called set reconciliation, or in a more relevant networking context, and they call it straggler identification. And basically it uses some ideas from math, from algebra, coding theory, to be able to concisely and efficiently represent a set of random packets that we've received in the middle of the network. Yeah, so we went deeper into this math and this algebra. We implemented a data structure called a quACK that uses these ideas. We highly optimized it so that it could be more practical to use. And then we made some considerations of like extra tricks we had so that it's more applicable and practical in this networking setting that we're using. Whereas previously, it's really been studied more in a theoretical context.
Yeah, Gina, I just jump in real quick and say, obviously there's some magical mathematical work happening there to make this thing kind of this work. But can you give us an intuition of kind of how that actually, the math behind it, and kind of what properties it's kind of using to actually, because like you say, kind of taking from the, I've got this totally kind of anonymized, encrypted set of packets I'm sending. How do I work out what the hell I've got given and say, yeah, I've received this? It kind of feels like an impossible problem almost. So like, how does the math help us there?
Yeah. Yeah, so some intuition. First, at a high level, how we're modeling this as a mathematical problem is that we have a data sender and then we have a proxy. So the data sender is sending some set of packets, S, and we represent each of these packets by a 32-bit packet identifier, which you can do by like hashing the payload to 32 bits or something like that. Mm-hmm. Okay, so that's a set S. And then on the proxy, or maybe like receiver of packets, we have a set R of all the packets that the proxy has received. And so we consider the set of packets R to be a subset of the packets of S. And so as a mathematical problem, what we're trying to do is figure out what is in this set R, or alternatively, what is in the set of S without R. So the set difference. Mm-hmm. And we're trying to find this at the sender, which already knows S. So finding either of these values is equivalent. And the way we're able to do this is eventually we're able to model the system of, or the set of missing packets as a system of symmetric polynomial sums.
And sounds fancy.
But back to just basic algebra, what we have is a system of, if we're missing m packets, we have a system of m equations in m variables. And all we had to do is solve this system. And that gives us an exact answer of which packets we're missing.
Awesome. Cool. So how did you then kind of, taking from this solution you developed, how did you go about evaluating kind of how effective it was? And yeah, what were the results?
Yeah. So before the NSDI paper, we actually had a hotnets paper. And the only thing we'd really implemented at that point in time was the quACK. And so we were like, what kind of performance guarantees do we need on this quACK in order to like make it practical to use? And one of them was that it has to be fast to encode. So every time you like kind of update the state of your quACK given a new packet, it has to be very fast. And it also has to be fast to decode. So every time you receive a quACK, it has to be very fast to figure out which packets are missing. And yeah, when we were writing the hotnets paper, one of our co-authors, David Zhang, he doesn't work in networking. He actually does more stuff with like high performance programming. So he really played a big role in, helping to optimize some of these like hardware operations for the quACK. But yeah, ultimately, because we found this algebraic solution and it's just additions and multiplications, these are all very fast operations on a CPU, and we're able to create a pretty good implementation of it.
Nice, cool. So tell us about the results, Gina. So like how quick is it? How good is it at decoding, encoding, and yeah, what are the overheads of it?
Yeah, so it depends on the exact parameters, but in the main experiment of our paper, it takes 33 nanoseconds per packet to encode a single packet into the quACK, and it takes 3 microseconds to decode a quACK at the end host.
Interesting. And is the asymmetry there? That's kind of why it's not the same either way. I guess, yeah, there's probably a reason for that.
Oh. Yeah. So encoding is much more important to be fast from our perspective, because a router or a middle box in the network could be processing a lot of packets at the same time, because it's not just your device's traffic, it's all the devices that are sharing the network. In comparison, decoding a quACK is at your end host, and your end host is probably just handling the connections related to you. And actually, the logic of like processing the information from a quACK, or even general acknowledgments, is much longer than actually what it takes to just decode the quACK.
Awesome stuff. Cool. So we've got our quACK then. So the quACK's component 1, that's technical challenge number 1 solved. So let's talk about technical challenge number 2 and something called Robin. And yeah, tell us what the challenge was and then how Robin solves this challenge for us as part of this Sidekick protocols.
Yeah. So Robin is kind of just our name for the system that we built around the idea of Sidekick protocols. So like what can we actually do in response to quACKs? Now that we have a Sidekick connection and we have the information from quACKs, what kind of what we call path-aware sender behavior can we implement in a sender so that it is giving us performance benefits that are, as good as what we were getting before with unencrypted transfer protocols and PEPs. And so kind of how we thought about this problem is, first, what kind of information are quACKs giving us now? quACKs are telling us which packets are lost, just like ACKs do, it tells you which packets are received, and then you determine which packets are lost based on that. it's telling you where this loss is occurring. So when you receive an end-to-end ACK, all you know is that somewhere along your end-to-end connection, a packet is being lost. But now that we have a quACK, we know, for example, packets are being lost on this near path segment to us, between us and the quacker. And we could even infer, like, based on that, which packets are being lost on the far path segment. Yeah, so we know which packets, we know where, and then also we know this signal a lot sooner. So for example, if in the train scenario, the router is quacking to you, then you can know which packets are received much sooner than if the end host, like all the way in another country, is telling you when packets are lost. So with these new signals, we think that we can get a lot better sender behavior, because now it's aware of things that are going on the path. Yeah, so then we thought about, okay, what are we actually changing in the behavior? And so we think about end-to-end ACKs. What do protocols like QUIC and TCP do with end-to-end ACKs? And so we kind of have four things here. One thing it does is it uses to retransmit lost packets. The second thing is it uses these ACKs as signals of loss and congestion, and it uses this to update the congestion control. The third thing is it updates flow control window. And the fourth thing is it discards packets, forgets them because they've been reliably received and we no longer need to do anything with them. Okay, so for quACKs, we ignore the fourth one just because for safety reasons, just because a quACK has received a packet, it doesn't mean that your end-to-end connection will have received a packet. So we'll really focus on the first three. Yeah, so for retransmission, what can you do? Well, now you know the packets are there. You know which packets are lost sooner. So if your protocol kind of wants you to have like low latency transmission, you can just retransmit the packet immediately. And in the case of QUIC for retransmitting a packet, so something that's a little different, if you're familiar with TCP retransmission, TCP will tell you that you lost, say, packet 7, and then TCP will just retransmit this exact same packet again, packet 7. But what QUIC does, so QUIC has kind of sequence numbers internally. These are not visible to any snooping proxies. So if you lose packet, say like 7 in QUIC, instead what it does, it kind of references the data that's in QUIC. And instead of retransmitting the exact packet, it's going to rebundle all this data in a new packet, possibly with other data that needs to be sent. And then it's going to transfer this over in a completely new randomly looking packet back to the end host. And so we wanted to follow like the spirit of QUIC. Instead of retransmitting the exact packet that was transmitted previously, we modify the client on QUIC to rebundle its data and retransmit the data in that lost packet back to the end host. So yeah, retransmission, it's not too complicated, because in the end, it seems like a lot of protocols just want to retransmit their data. Although that's not true if you have like some more lossy media protocol. But this is kind of how we thought about retransmission.
Cool, nice. So yeah, so I guess given retransmission, how did it handle sort of congestion and other signal for sort of congestion control as well? Did you use the quacks in that? By the way, I love the fact that it's called the quackers and you're referring to it as quackers. I think it's brilliant. It's an awesome name. Yeah. So how do the quacks help on the congestion control side of things?
Yeah, on the congestion control side of things, consider the train scenario. Why really is your connection slow? And it's not just that you're not retransmitting things fast enough. It's because your laptop is like, it thinks because there's so much loss occurring that it thinks that it's in congestion collapse, basically. Because loss is occurring, it keeps sending slower and slower, but the same loss is still occurring. So it just keeps sending slower. And because it does this, then your connection is really slow.
The exponential back off. It's like, oh, this is falling. Okay, I'm going to try again in an hour. I'm going to try again in 2 hours. I'm going to try again in 3 not hours, but obviously, yeah. So okay, okay, cool.
Yeah, so it's really not a retransmission problem. It's a congestion control problem. Mm. And just to give a little background more on TCP PEPs, the reason that the way that PEPs help here is that they don't just retransmit the packet sooner. A TCP PEP in this scenario could actually be splitting the connection into 2 completely separate connections. And so it has like one connection for the short lossy path, and it's sending signals about loss very quick. And then it has the other side of the connection that it knows it can tell it's more reliable, and it's like just keeping it more saturated over time. And so the way we integrate this into quACKs, kind of at a high level, is that quACKs are now telling you where the loss is occurring. So now you know that you have like a really short segment where all the loss is occurring, and then you have a really long segment where actually you're not really losing that many packets. And so that kind of helps you, still be, you have to update your congestion control. You can't just like retransmit the packet without doing anything to congestion, because anytime you're just adding more data to the wire without kind of considering its impact on the connections around you, that might not be fair. And so our goal here was to mimic the behavior of a TCP PEP in how it's handling congestion. And so we're using the signal about where loss occurs to kind of think about our congestion window and pace and sending rate of packets to be, just as fair as TCP PEPs, but also as fast as them. And I don't know if this is like the right answer for congestion, but definitely the main takeaway I want is that, we have more signals now that we could incorporate to have, better, faster, but still fair congestion control in our networks.
Nice. Yeah, it makes total sense. So how does Robin perform then? So yeah, what's the how good are the results? Tell us about the results and the experiments I guess you ran as well to get the results.
Yeah. The main experiments that we ran is, so that train scenario, we didn't end up writing a train, unfortunately, but we did set up a router or access point in our computer science building, and then attached a cellular modem to it to emulate that like cellular connection. And then I sat like, a few feet away from the router so that the Wi-Fi wasn't as good. And there were like people in the office, so there was probably some interference as well. So we had like a short lossy network, and we had a long, more reliable network. And so we tried uploading a large file with QUIC, and then we were able to improve the speed of that upload by about 50%. Wow. And then we also kind of implemented a simple media protocol to test whether, we could have better latency. And so the exact metric that we measured is dejitter buffer latency. So if on the other end of your audio stream, you kind of have to wait for the packets to arrive so that you can play them in order. And then the dejitter delay is how long your packet has to sit in that queue before you can play it. We were able to reduce it from 2.3 seconds to 204 milliseconds, which is about 91% reduction.
It's a big reduction actually. Yeah. Awesome. Cool. So yeah, I mean, we've heard about quACK, we've heard about Robin, and there's one last component in your paper that you talk about, and that's, I don't know, it's PACUBIC or PACUBIC. I don't know how to pronounce it, but yeah, cubic with a PA in front of it. So yeah, tell us what that means and what's it trying to solve and how it solves it.
Yes. I guess I would call it PACUBIC. You can say it however you want. It's fine if it's funny.
PACUBIC sounds good.
Yeah, so I kind of talked about this. This is kind of integrated with the second challenge.
Okay.
In that it's just it's a new kind of congestion control algorithm that integrates information about where loss is occurring on the path.
Nice.
Yeah,
cool.
and yeah, we don't know if it's the right answer for sure. And there's a long appendix in the paper kind of going more into the theoretical side of it, but I do think it's really exciting that we can have more signals that could
definitely
inform behavior on the end host, including congestion control.
Yeah, I guess that's a nice segue then into the sort of the future directions for Sidekick protocols then. And yeah, where do you go next with this? Is it exploring the angle and sort of seeing how you can combine all these different signals together to make even better, smarter, fairer, quicker networks? Yeah, what happens next, Gina?
I think some interesting things could be, if you want to make it practical, and then also, is the quACK the right signal? Are there other signals from the middle of the network that we can incorporate to Sidekick protocols? Now that we have a quACK, or kind of a more practical implementation of these ideas from straggler identification or set reconciliation, are there other networking settings in which this kind of information could be useful? But really, what I am really thinking about right now is, Sidekick protocols only send information from the proxy to the data sender. But if the bottleneck of that link was actually on the other side of the proxy, then Sidekick protocols are not really helping. And yeah, so right now, Sidekick protocols are awesome. They can do lots of things, but they can't do everything that PEPs can do. And so I want to make Sidekick protocols as good as PEPs. And I think one of the things that needs to be done possibly is we need like buffering or a generic way to think about behavior at the proxy. But just, yeah, next steps so that there's kind of no reason not to replace PEPs with Sidekick protocols if Sidekick protocols can do everything that existing PEPs can do.
Yeah, nice. It definitely kind of reduces the barriers to adoption, right? If it's a clear win on every different metric, however you wanted to sort of to view the comparison between the two, then it's going to definitely help adoption and have a bigger impact, I guess. So yeah, I don't know if this is a valid question, Gina. So excuse me if it doesn't make any sense. But can you have a quack between quackers? Can you? Because at the minute you've kind of got this sort of end host, and then the like in your train scenario, it's the router on the train, right, or whatever it's there. Can you have quackers all the way along your path who are then communicating with each other and also then making you then the proxy itself can leverage these signals as well rather than just the end host? Or is that sort of again breaking that sort of model of end to end, I guess?
Yeah, it wouldn't. Yeah, so imagine if you have like an end host and then two quackers between you. So now if these quackers are quacking to you, the data sender, you can learn like not just whether loss is occurring on like the near path segment or the far path segment, but like which of these three or any number of path segments. So, one concept is that you could be, you have even more information about the network. Now, at some point, I guess there's probably diminishing returns about more information about the network this way. But yeah, that's definitely a possibility that could merit more exploration.
Cool. Yeah, just quacking between quackers. I don't know. Just kind of came with like, I'm going quackers. I don't know. There's a joke in there, something.
Quackception.
Yeah. Quackception. There we go. It's quackers all the way down. Cool. So we touched on impact there slightly and sort of trying to ease the kind of the barriers to adoption and making this a clear win over the current state of the art of how things are done. So I guess, yeah, what's your take on this and sort of the impact you think Sidekick or the impacts you wish it can have or maybe already has had kind of going forward?
Yeah. I know one of your goals of this podcast is to connect research to industry people. And I think, this is where industry people could definitely, have an impact. So sometimes I think about like what, me and my co-authors, we think about what it would take to make Sidekick protocols real. And I think one of the things we need is interest from the parties that would be involved. And so the parties that are involved in a Sidekick protocol kind of are the people who send data. So this can be like video streaming companies, CDNs send a lot of data, anyone who develops your browsers and are used by, just day-to-day users who are sending data. The other party involved is what we've been calling the quacker, the proxies or the middle boxes. So I think, satellite companies could find this interesting if they find that all their users have been switching to QUIC and they're not able to give as good performance as before. Cellular companies who are deploying TCP PEPs along their path and also finding similar behavior. Anyone who manages their own like internal network and kind of deploys performance enhancing proxies. Yeah, anywhere that TCP PEPs exist now and are finding that like the people who are using their network are using a lot more of the secure transfer protocols. So we really need like interest from these people involved before you start like just bombarding people with like signals about your network. So yeah, just like getting the idea out there and like people thinking, maybe this could actually be a solution to their problems. And then, yeah, kind of a third perspective is, internet standards people. And these are, the awesome people that write these very detailed RFCs and, garner interest from other internet standards people and come together to like create, like this like just wonderful, very detailed document so that, everyone's on the same page and we can kind of be confident that it will work. And, luckily one of our co-authors, Michael Welzel, is very involved with the IETF. He's been bringing Sidekick, previously Sidecar, into these discussions and kind of like thinking about how it would fit in with what people are talking about in that community. yes, there's lots of things that we did not address in this paper that are needed to make Sidekick protocols practical. And that's like, discovery. How can the two ends of the Sidekick connection discover each other? And then how can we do it securely? What other security mechanisms do we use? Maybe like what other signals can we send? Just very like practical things that need to be addressed before it will really happen.
Yeah. Yeah, and actually, there's a lot of stakeholders there, but there's a call to action there that's part of the podcast. Hopefully, someone somewhere listens to this and kind of goes, oh, actually, maybe I should check these Sidekick protocols out, and it can help you sort of realize that goal of getting these out there. And I mean, at the end of the day, we all want, as an end user, as a consumer, we all want like faster, more reliable networks, right? So if this is going to get us there, I mean, like it feels like a no-brainer to me. But yeah, I guess there's a lot of work needed to be done to make it practical. But the early signals are definitely very positive, right? In fact, this is a very viable approach. So yeah, awesome stuff. Let's change gears a little bit and talk about some surprises that you found while working on Sidekick. So yeah, I guess the question is, what's maybe the most interesting lesson that you've learned while working on this type of protocols and in this space, maybe?
Yeah, I think prior to this project, I wouldn't have really considered myself a networking person.
But you've been converted now. You're a networking person now, Gina.
And now I feel it. But I think working in systems or networking or these computer science fields that have been around for relatively long now, at least for computer science, it's not exactly LLM, but there's a lot of history to these fields, especially in systems. And yeah, even though I have vague memories about dial-up internet from back in the day, I definitely grew up in an age that was way past that. And so I think working on this project, and then now that the project is out and I meet a lot of people who are interested in this project, it's really awesome to have like a different perspective on the internet and the network from people like my advisors and collaborators and just other people out there who have lived through like the development of TCP and the frustrations of PEPs, and then reflections on like from the inventors of QUIC, or just about the early internet and like what it has evolved to today. Like people have very strong feelings about even the definition of middle boxes. Like people would probably feel very strongly in the way that I'm using that word middle boxes. And it's like so interesting that like, because people grew up in this different time, that there's like all these emotions attached to like how this field has changed over time.
Oh, yeah, it's interesting. I mean, I'm going to probably date myself a little bit here, but I remember dial-up internet. I mean, the first computer we had in our house was dial-up, and I remember it being like, obviously there's the noise that goes with it, right? And if someone else was on the phone when I was on the laptop, on the computer, then the connection would drop, right? So I'd be like, Mum, get off the phone. I'm trying to play, I don't know what stupid video game I was playing at the time, but safe for the internet. But no, that's really interesting to kind of get people's take on it, who've kind of lived through the whole sort of development of these things that kind of a lot of people kind of come into the world today, right? You just kind of, the internet exists, right? But there was a time when it didn't, which kind of is hard to get your head around, I guess. But yeah, cool. Let's talk about the origin, because you mentioned it earlier on when we were chatting about the origin story, and we might get into this a little bit later on. So maybe now is time to do that. So yeah, can you tell us about origin story for the paper and like some backstory? So how did you arrive at the Sidekick protocols?
Yeah. So at the time I was working on I think the origin story starts from before this project was even in my head. I was working on something kind of very different. It was kind of, I wanted to be able to audit the logs of a router that may be trying to hide its malicious traffic. And so I was working on this with David Mazieres and Matei at the time. And we kind of distilled it into this mathematical problem, which is this set reconciliation problem that I mentioned before. You have a set S and a set R, and how do you communicate the least amount of information to find the subset? But actually at the time, I didn't know anything about set reconciliation. I was kind of just like deriving it and forming it as like, a mathematical problem, kind of with some suggestion from Dan Bonnet, another professor in the department, on how to do this. And the three of us, we were more like systems people, and we're kind of just like, just trying to figure it out. And then one day I was like, I had this like piece of paper on my desk and I had this like set of polynomial equations. And I'm like, how do I solve this? I have no idea. Google isn't really helping me. And then just another grad student, Matthew, one of the co-authors on this paper, like wanders in and it's like, what's up? And I'm just like, I have this hard math problem. And then he likes math. So then he takes this problem, he like goes, talks to his friend down the hall, David Zhang, who ends up being another co-author on this paper. And then, he also likes math. And then they take it to like some like math mixer and they talk to some like math PhD students and they come back like, we have an answer to this. And I'll keep rambling a little bit, but the end conclusion is going to be, this touched a lot of people to get to where it is, even if it's just like a sentence in the hallway. And then, Matthew and I in particular worked a lot on like the implementation of once we figured out this like algebra, we worked on like, making it work with this router that we had and like real packets and like in a real networking setting. And we like scrapped up some paper that was rejected about this like malicious router stuff.
Yeah.
And then in like the very last minute, we kind of discovered this whole body of like related theoretical work that is solving this problem that we thought we had just like solved. So now we're like, I don't know if I can swear on this podcast.
Yeah, go for it. Fine, yeah.
Then we were like, shit. And then we like talked. Then we went downstairs to the first floor to the theory department. We talked to Mary Wooters, who's, she does a lot of research in coding theory. And it's just like, it just makes sense to her. She just knows this stuff. But of course, like her perspective is like from the very theoretical side. And so like, we felt like, oh my gosh, this has already been done. But also we felt like there's still something there, like, networking and theory. It's like very different, kind of bringing like to these two worlds. Their side of the problem is so obvious, but you really need to connect them in order to get the solution. But now we realize that, there's stuff in coding theory that exists. And so, this is how the math of the quACK came about. Now, on a very separate branch. so Keith Winstein and Michael Welzel, both authors on this paper. Keith is professor of computer science at Stanford. Michael Welzel is professor at the University of Oslo. And he's also, as I mentioned, very active in the IETF. So I think Michael is very much more in like the IETF community versus Keith is in like this networking research community. And even though they're both on networking, they're actually also quite disjoint. But anyway, they ended up talking somewhere and then they came up with this idea of what was previously called the sidecar protocol, where you send information about the network instead of manipulating the data. And so they had this idea of a sidecar protocol, but they were always stuck on like, how can we send the right information? Like we're either always sending too much information or it'll take too long to figure out this information. And so they were kind of just sitting on this idea. And so I don't know, I think one day I was just talking to Keith because we just passed by each other or something, or someone told us to talk. And then he's just like, I have this like terrible problem. And I'm like, I think I have a solution. He's like, no, you don't understand. It's like such a hard problem. And I'm like, but I think it works. And he's like, I don't think it'll work, but whatever. And it's like, and then I'm like, I think it works. And so honestly, I think we had to like, really implement it and like bring it to him before he was like, oh yeah, I think.
I needed empirical evidence to prove him to like, okay, now I believe it.
Yeah. And so long story, but I think it's just amazing that if you connect the right people at the right time, then like something wonderful can come out of it. Yeah. And it took a lot of, it's like a lot of just like chance that like, I think the people from theory, from networking, from systems that, once we combine it all, then we have this like really cool paper. And I didn't talk about the last co-author, David Mazieres. He really helped, I think, you zoom out in this project and help us think about Sidekick protocols as more than just like helping QUIC, but, really helping any transport protocol and just like zooming out and thinking about, how this can really have the most impact.
Yeah, that's a lovely story to see how. I mean, there's a huge elements of serendipity to that sort of like, yeah, I bumped into this person in the hallway, and then colleague came in one day and said, "What you working on?" And then took it to some math mixer, and then they figured it out, and that sort of whole journey is lovely to see. And you know, and it's like it's a really nice sort of illustration of how I think research should work in a way, and that you're in that environment surrounded by people from the fact that you can just pop downstairs and be speaking to someone who's an expert on something, like who's it's kind of tangentially related, but then you put those two people together and you can create like this really cool paper out of it. And it's great to see that it's a culmination of like numerous individuals as well, and all bringing their own strengths to the table to produce, yeah, a really awesome piece of work. So no, that's really nice origin story, that, Gina. I guess this kind of leads into my kind of next question. As long-time listeners will know, this is my favorite question about the creative process and how you approach that the act of creating really cool ideas and generating ideas and then selecting which ones to work on. So can you maybe elaborate on how you do that?
Hmm. I was thinking about this and how I would describe myself. I think I've heard many times it's important to pick impactful problems, but I actually just like interesting solutions. And interesting doesn't mean complex. And I guess it can be very subjective. So what's interesting to me? So I feel like maybe one way to solve a problem is you stare at the problem for a very long time and you kind of branch out from there about like, yeah, what others have done, or, you know, what might be like a natural first solution. And yeah, this is important to explore, of course. But I think the interesting stuff to me comes from kind of if you can develop knowledge bases in more eclectic areas or different areas, at least enough to draw connections between those, it's kind of, then you get the like kind of unexpected connections, or kind of when someone goes like, oh, that's interesting, because then it's just not something that you expect. And that kind of little sense of astonishment is kind of what makes things interesting, I feel. But it's always important to go deep at some point. And so possibly, you know, after those connections have been made. But this is like, I don't know if this is a research philosophy or life philosophy. I think it's fun to go broad and to always be learning, because you never know when something that you learn is going to be used in your life. And yeah, that said, I don't really have a formula. I feel kind of chaotic sometimes and just like pursuing the thing that's like right in the moment. And then hopefully, like, as long as you're always pursuing something, at some point it'll circle back and then
Yeah.
it'll all make sense. So
No, I love that. I love that, how it's like, it's not necessarily a research philosophy, but like kind of a philosophy for a way to approach life in general, right? I think being creative, and like they're kind of one and the same almost. I think that these two sort of things, but I love that kind of just, it's like trying new things, like, all the time, because you never know whether you're gonna kind of encounter something you really enjoy or like doing, or have this great idea, and you only do that by exposing yourself to new areas and new things, right? So yeah, no, that's a lovely answer to that question. Another one for me to add to my collection. Cool. So Gina, we've come to time for the last word now. So what's the one thing you want the listener to take away from this podcast episode today?
mm-hmm. Well, for Sidekick protocols, my main takeaway would be there can be a world where performance enhancing proxies and secure transfer protocols coexist. But in general, I think the takeaway is, if you want to learn about Sidekick protocols, you could probably also just watch my conference talk. But I hope from this podcast, or just in general, I hope listeners can have learned something interesting in kind of the origin of the story or the people behind the story, and in general, just learning about like the background behind all of these wonderful research ideas and papers that are out there.
That's great. Great message to end on. Thank you so much, Gina. It's been a fascinating chat today. I've really enjoyed it, and I'm sure the listener will have as well. Where can we find you on the social media or anything, or where can listeners connect with you to find out, keep up to date with all the cool research you're doing?
I'm not super active, but I have a website and my email is on that website, and I always love talking to people.
Cool. awesome stuff. We'll put links to everything we've mentioned today in the show notes as well, so you can go and check that out and learn more about Sidekick protocols and, as I say, all the cool research Gina's done and will continue to do over her career, I'm sure. And yeah, we'll see you all next time for some more awesome computer science research.